Assalamualaikum warahmatullahi wabarakatuh and hi. My name is Nurul Ashkil Minti Rahim and my matrix number is 205310 and my group member is Kartik Varman and Alaki Surimurti. Matrix number 205806 will present about the applications of differential equations for the group project. So I will present about the Newton's law of cooling and the decay equation, while Kartik will present about the exponential growth model and RL circuit. Now I will present about the first application, which is the exponential decay for radioactive material. So the characteristic of this equation is an ODE, a non-homogeneous equation, first order, and a linear equation. Okay, first let MT to be the amount of a product that decreases with time, and then the rate of decrease is proportional to the amount of M. So we will get dm over dt equals to negative km. And then we solve the above first order differential equation. We will obtain MT equals to AE power of negative KT. And then we assume that M equal to M0 at T equals to 0, and then we assume that M0 equals to AE power of 0, which gives A equals to M0. And the final equation will be MT equals to M0 E power of negative KT. So here I attach a graph for the decay of a radioactive substance for this application. Next, for the second equation, which is Newton's law of cooling. The characteristic of this equation is ODE, a non-homogeneous equation, first order, and linear equation. So the law states that the rate of change of the temperature is proportional to the difference between the temperature T of the object and the temperature TE of the environment surrounding of the object. So the first equation we get dt over dt equals to negative k T minus TE, and then we will let x equals to T minus TE, so that the x over dt equals to dt over dt. And then using the above that we have changed, we will get dx over dt equals to negative kx. And then the solution for the differential equation is given by x equals to ae power of e kt, and then we will substitute and we will get t minus te equals to ae power of e kt. And then we will assume that at t equals to 0, the temperature T equals to T0. So the equation would be T0 minus TE equals to AE power of 0, which give A equals to T0 minus TE. And then for the final expression for T is given by T equals to TE plus TO minus TE E power of K negative KT. So for the last equation, it is show that the temperature T of the object changes with time.
Good evening, Doctor. My name is Kartik Varman and I'm Lucky Suryamurthy, matrix number 205806. And today I'll be explaining the application of differential equation in RL circuit and also exponential growth curve. So what is an RL circuit? RL circuit is basically just a basic circuit which has resistor and also L, which is inductor. So let's have a look of the basic terms that has been used in this situation, this application. V is supply voltage, I is current, R is resistance, and L is inductance. So how do we come up with this equation of this final equation here, which is Ri plus L di over dt equals to V. So based on these two laws, which is Ohm's law and Faraday's law, we can have these basic terms, which is Vr equals to Ri, Vn equals to L di over dt. So with these basic terms, we can use this basic equation to substitute the terms inside these known laws. So with that, we have substitute and we have a final equation, which is Ri plus L di over dt equals to V. So with this is our differential equation for the RL circuit. And let's have a look of the characteristic of the equation. Okay, first, we can say that it's an ODE equation. Okay, so why do we say it's an ODE equation? Because there's only one independent variable, which is t, also known as time. Okay. Secondly, it's a non-homogeneous equation because the equation doesn't equals to 0. So this is that. And third, it's a first order equation because the degree of the derivative is 1. Okay. Fourth, you can say it's a linear equation. This is said because the the dependent and dependent, sorry, not independent, yes, the dependent and their derivative doesn't occur as product, and the highest degree is also known as 1 only. Okay, so let's move on to the next slide. Okay, with this next slide, I want to explain about exponential growth model. Okay, so this is another situation where differential equation comes in play. So for this equation, we have dp over dt equals to kb, where a and b are constant. So a is a birth rate and b is death rate. In this situation, for exponential growth model, we can assume that these two conditions are constant. So let's have a look. K is a constant rate of growth. So with this equation, let's have a look of the characteristics of the equation. It doesn't differ from the first at all. It's just an ODE equations. I can see here the independent variable. There's only one independent variable, which is t, also known as time. And then the second, which is non-homogeneous, as you can see, the equation doesn't sums up and equals to 0. The third is a first order equation. Okay, why do we say it's a first order equation? Because the highest highest degree of the derivative equals to 1. Okay. Fourth, it's a linear equation because the dependent or their derivative is doesn't occur as a product. Okay, and the highest degree is also 1. Okay, that's it for me, doctor. Thank you so much. I'll stop here. Thank you, doctor.